Hey, I'm Lauren White. In this lesson, we'll talk together about how to recognize enantiomers. All right, in previous videos, we've talked a good bit about what chirality is, being mirror images but not superimposable, like this atom here. Remember, the dotted line is our mirror. They're mirror images, but no matter how we rotated them, we can't lay one on top of the other and have the groups line up. Well, we can get even more specific when we talk about pairs of molecules that have chiral carbons in them. We can name them enantiomers or diastereomers. We'll talk about diastereomers in another lesson, but enantiomers can be, as we see with this, a molecule with just one chiral center, or it can have two or more chiral centers. The key to enantiomers, though, is that they must differ at every chiral carbon. Well, what do I mean by this? Well, they have to be connected to the same atoms, but the way those atoms are arranged in space, the RS designation, must be different at every single chiral carbon. So in the molecule we're shown here, the one on the left is R and the one on the right is S. Well, there's only one chiral carbon in each and they are different, so these are enantiomers. If we had a molecule that had two chiral carbons, then the one on the left would have to both be R and the one on the right would have to both be S for them to be enantiomers. You won't always be given the RS designation at each chiral carbon, so to identify if a pair of molecules are enantiomers, you need to determine the RS designation if it's not given, and if they're different at every single chiral center, then they are enantiomers. Let's do some examples. Notice the RS designations aren't given to us for any of these, so we may need to find those. All right, part A. Are these molecules mirror images? Well, they may not look like it now, but if we were to spin the molecule on the left, we could redraw it such that they are mirror images. And this is a good point to make. If the molecules don't appear to be mirror images, you may need to do a little bit more work. Now, if they do look like mirror images, you can quickly check to see if they are non-superimposable, and if those two things are true, then they're enantiomers and you're done. But in a case like this, the best way to go forward is to say, are they connected to the exact same atoms? Well, yes, they are. The carbon in the middle is attached to a hydrogen, a CO2H group, a CH3 group, and an OH group in both cases. And then we'll need to go through and figure out the RS designation to see what that is for each molecule. If they have the same designation at each point, well, then they're just the same molecule. If they differ at every point, though, then they're enantiomers. Okay, let's number our groups by priority here. Oxygen is the highest, so that OH group is first. Then this CO2H group, since its second atom in line would be an oxygen, our methyl group is third, and our hydrogen is fourth. Same thing for the molecule on the right. OH, then CO2H, then the methyl, then the hydrogen. Notice, though, that our lowest group, the hydrogen in this case, is on the top. It's not on a dash or a wedge. So we need to flip the molecule so that the hydrogen is in the back. And this rotating of molecules in your mind is not easy to do. So if you haven't already, check out a previous video for a deeper explanation of the trick we're going to use here to make these into Fisher projections. So we want to imagine that we're dancing with this molecule, and we're going to step in between the wedge and the dash, and we're going to take our partner's hands. And so into our left hand would be this OH group, so we put OH on the left, and into our right hand would be the CH3 group, so we put a CH3 group on the right. We look up into our partner's eyes and we see a hydrogen. We look down to make sure we don't step on their feet. We see a CO2H group. Perfect. Now our priority doesn't change. Oxygen is still first, CO2H is still second, methyl's third, and hydrogen is fourth. So now we can draw our circle. We start with the first priority, this hydroxide. We go over our second priority to our third, and then we're drawing our circle counterclockwise. So we temporarily want to call this S. And then we need to check our lowest priority group, that hydrogen. Is it going into or out of the page? Well, it's on a vertical line, and in Fisher projections, that means it's going into the page, which is exactly what we want. We do not need to change our designation. This molecule is S. Now, we could do the same thing for the molecule on the right. We can step in here to dance with it, and we take those molecules into our hands. In our left hand, we're going to have a CO2H group. In our right hand, we will have a methyl group. We'll look up and we'll see a hydrogen, and we'll look down and we'll see OH. And again, our priorities stay the same. And then we want to draw our circle. So we start at this OH, we go to the second priority, we skip right over that fourth one to the third priority. We are drawing this in a clockwise direction, so temporarily we call this R. We need to check that lowest priority group. Again, it's on a vertical line in a Fisher projection, which means it goes into the page. So this molecule is R. Since these molecules have only one chiral carbon, and one is R and one is S, these are enantiomers. All right, let's look at the next two examples. Do these molecules look like mirror images? We can draw a mirror right down the middle, and yeah, they're clearly mirror images. Are they superimposable? Well, no. No matter how we tried to spin the molecule on the left, we could not make it look like the one on the right. In fact, if we tried to move this NH2 so that it's on the left, then we would have to spin this molecule around. And remember what solid wedges mean. They mean that molecule's coming out of the page at you. So if I were to spin that molecule on the left around so that my NH2 is on the left, well, now that NH2 is on a dash and going into the page. So these are mirror images, but they are not superimposable, so they are enantiomers. As it turns out, if you go through and prioritize your groups and draw your circle and check that the lowest group is in the right place, then you get that both chiral carbons on the left molecule are R, and both chiral carbons on the molecule on the right are S. So they have two chiral carbons and they are different at every chiral carbon. So they're enantiomers. All right, part C. Do these molecules look like mirror images? Well, again, we can draw our mirror in, and no, not quite. On the bottom, they certainly look like mirror images, but on the tops, they're actually just the same. So these two molecules then cannot be enantiomers. And again, if we went through and found the RS designations, what we would find is that in the molecule on the left, the top chiral carbon is R and the bottom chiral carbon is R. And the molecule on the right, the top is R and the bottom is S. Since they do not differ at all chiral centers, they are not enantiomers. So keep in mind that if you can quickly see that they are clearly mirror images or they are definitely not mirror images, then you may not need to go through and find the RS designations. But if you do, the easiest way to do that is to make a Fisher projection. Now, you should feel more comfortable recognizing enantiomers.